Welcome back to the training series for the Rehabilitation Cost Estimation Tool for mining and exploration in New South Wales. This is Module 10. The Water Management Area sheet calculates costs for decommissioning and rehabilitation of water storage structures like dams, ponds and basins, and for water treatment including acid water and saline water. The pond default costs are divided into type, process, raw, and evaporation, size in megalitres, and by land type, native, pasture, and arid. The costs for type vary depending on the amount of sediment we assume needs to be removed. These assumptions are shown in the Assumptions General sheet. The default sections include tables for decommissioning and rehabilitation of several types and sizes of ponds, refurbishment of ponds if they will be retained, removal of sediments, pontoon removal, load and haul of water and brine, treatment of low pH water and saline water, decommissioning and removal of water treatment plants, and pumping and transferring water. The User Build section is for pond removal only and includes tables for removal and disposal of sediments, pushing in bunds and backfilling, removal and disposal of liners, and land rehabilitation. The default section of the sheet has several ways to enter quantities for ponds. The first set of rows lists all the pond types and land types available in the tool. If the user has one type of pond, they could just use the first section. Select your pond, let's say a raw water pond of 10 megalitres where the land must be rehabilitated to native, and enter the quantity, let's say we have 2. If you have other types of ponds, you can enter them into these same rows going across the columns. The next set of rows group the pond types, process, raw, and evaporation, and allow the user more flexibility in selections. If you have many ponds of different types, you may wish to use these sections. Let's go across to the next empty column and enter a variety of ponds. Let's say we have 3 process water ponds of 2 megalitres size in a native vegetation area. We have 2 evaporation ponds of 120 megalitres also in native vegetation. We can enter ponds of the same type and of different capacity in other columns. Let's add another evaporation pond in the adjacent column that is 55 megalitres in native vegetation. For this pond, we have an engineering cost estimate that says the pond can be rehabilitated for $280,000, so we add this and provide a comment for the regulator. The next section has default rates for stormwater or clean water ponds that will be retained and the cost for refurbishment. There are 2 options, small and large. Small ponds are typically less than 0.5 hectares and large ponds greater than 0.5 hectares. We have 10 small ponds and we will enter these to the first column and 2 large ponds which we will enter in the adjacent column. The next section is removal of sediments to make a clean water pond. This table is likely to be rarely used as the costs for sediment removal are included in the default pond costs. An example may be a very large pond which will be cleaned out and used for clean water and doesn't reasonably fit into the clean water retained section. To use this section, we just enter the volume of sediment to be removed and select the distance to which the sediment will be hauled for disposal. The last section in the ponds table is removal of pontoons. This item is just for pontoons that will be removed from the ponds that will be retained without any further work. The next sections are management of water and brine. If using this, we are encouraged to explain how water and brine volumes are calculated or forecast and how they would be managed. The default pond rates do not include cost for management of liquids, so quantities must be entered here. It may be acceptable to show that water would evaporate or be beneficially used. The next sections are for treatment of water and has options for adjustment of low pH water and removal of salt and general pumping and transfer of water. The default pond rates do not include cost for treatment of water, so quantities must be entered here. Correction of low pH water assumes the use of neutralizers. Removal of salt is assumed to be by reverse osmosis. We have 1,000 megalitres of low pH water and 500 megalitres of high salinity water to manage, so we enter these quantities into separate columns. Water management scenarios will vary from site to site depending on the mine type and degree of processing undertaken. We need to provide sufficient information to support the determination of volume of water and/or brine and/or water treatment options, which will be informed by water quality results and an understanding of the mine processes. The pump water transfer rate allows for water that must be managed and is not included in other rates. The default rates for treatment include an allowance for pumping, so do not need to be entered again here. The user build table for the water management area sheet gives us more flexibility on the inputs and allows site-specific area entries, including pond geometry, example length and width of walls or slope of walls, the sediment thickness, area and thickness of growth media placement, and a wide range of fleet selections. This table is more complex and requires us to enter all the appropriate quantities to allow a proper cost to be calculated. We must enter quantities to the following tables: remove sediment, push in bund, liner remove and dispose, source and apply growth media and ameliorants, revegetation, and maintenance of rehabilitated areas and repairs. Let's go through a user build example for an 80 megalitre dam containing raw water in an arid environment. We first enter a name, like Raw Dam A in this case, and any notes that will assist understanding. We will add Raw Water Dam in Mine Area A. The first selections are for the type of dam and whether there is a liner. We select Dam Raw and Lined for our example and enter the volume of 80 megalitres. A warning may appear in the volume check row, and this is because we are yet to enter quantities that will calculate the size of the dam. The next few quantities determine the volume of soil in the bund walls to be managed. We enter the slope of the walls, which is typically between 2 and 4. That is, if the height of the wall is 1 metre, the width of the toe is 4 metres in the case of a 1 in 4 slope. The bund wall height above ground is the height of the bund above the surrounding land surface and is 1.1 metres in our case. The bund width at the top is the flat surface of the bund upon which personnel walk and/or vehicles drive. Our width is 0.7 metres. From these quantities, the tool calculates the cross-sectional area of the bund above the ground surface, which is later multiplied by the perimeter to get the volume of bund wall to be pushed in. The next few quantities also input into the bund volume and to the void remaining to be backfilled once the bunds are pushed in. The height from base to crest surface water level is the perpendicular line from the base of the pond to the dam crest. Ours is 2.2 metres. Our base length is 176 metres. From here, the tool assumes a square shape to calculate the base, the other side of the base, the side of the crest, and the crest level surface area. The tool uses these parameters to calculate a volume, which is a check on the quantities entered. The tool calculates the water storage volume based on the user inputs and posts a warning if the calculated volume is different to the user-entered capacity by more than a threshold. That threshold is shown in the assumptions general sheet and at the 1st of October 2025 was set to 20%. In our example, we are within the threshold, so you can see the warning is now gone. We will come back to the bunds. The next section, though, is removal of sediment. Remember, the default assumption for sediment thickness in a raw dam is 0.3 metres, so if we enter anything less, we should enter a note for the regulator. In our case, we know from gauging of the sediment and modelling that a reasonable sediment thickness to enter is 0.4 metres. For a large dam, a medium fleet may be used, and in our case, we will transport sediment 5 kilometres to void for disposal. We now come back to the bunds. The tool has calculated the volume of soil in the bunds that can be pushed back in to backfill the dam void. If there is insufficient volume to backfill the dam to the surface, the deficit volume will be shown. In our case, over 70,000 cubic metres of soil is required. However, in our example, we have studies to show that a depression can be left where the dam currently resides and drainage and erosion will not be an issue. Our studies show we still need to backfill 30,000 cubic metres, so we override the 70,000 with our 30. We have a stockpile of suitable backfill nearby and will use a medium fleet to load and haul. The next section is for liner removal and disposal. The tool applies a fixed multiplier to the dam footprint to estimate the liner area. If unlined was selected back in the first section, the area for liner is automatically set to 0. The tool applies the specific mass assumption in Assumptions General Sheet to calculate the mass of liner to be disposed. The one-way distance to our disposal centre for plastic liner is 210 kilometres, so we select the 200 to 250 kilometre category, but we have a quote for transport and disposal of the liner. To realise this quote, we set the transport cost to 0 by entering 0 here, and we enter the gate fee, including transport cost, to the gate fee alternate rate. Our quote is 82 per tonne, including transport, and we must then provide a note to the regulator. The next few tables are for land rehabilitation and are populated similarly to the other sheets. In our example, we are in an arid environment and do not need to undertake any land rehabilitation. We must set the area in each of the tables like this to ensure no costs are added for land rehabilitation. In our example, we have to undertake land management of 20 hectares of undisturbed land, so we add to the Maintenance of Rehabilitated Areas and Repairs table. As usual, we can add additional items to this table. As for all the sheets, the subtotals for each table are shown in the black lines at the end of each section, and then the total for each column is shown at the top of the sheet. The total for the sheet is shown on the left-hand side, and then above that is the total for the entire RCE, so we can see in real time how quantities entered to the local sheet affect the total RCE. Let's jump over to the RCE summary to see how the total is building up. As we can see, we now have rolled up costs for infrastructure area, infrastructure mine entries, beneficiation facilities, tailing storage facilities, and water management.